Okay. Ding, 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 ding. I found a remote control here. Does that work? Press the mute button. Yes, almost. Oh, the infrared is working there. Good, excellent, good. Thank you for your attention. Well, welcome to our weekly talk shop here on anatomy, physiology of hearing. 5 weeks in, we're talking about loudness, which is arguably the most effective measure that we can take in order to help hearing impaired people. And I'm going to give a little bit of a background here, which is partly a repeat. I'm repeating some of the things just to make clear that they come over more clearer. But now everything is broken. Ah, here we go. It just thinks for a while. I apologize also, there are 3 or 4 slides in here that are not on the Blackboard one. They're on the Blackboard one now, but I have sort of upgraded it over the weekend because I did get into some reading, which is always interesting, because you find out that in the year that since you've given that talk last time, or longer in that fact actually, there's some other things that have come up, and the science that you thought is true is not necessarily still true. So, learning outcomes today, we're learning about loudness, we're learning about the definition of loudness, loudness contours, the physiology, how we measure loudness in our auditory nerves, and most importantly, how we perceive loudness. 2 ways of measuring loudness, one is scaling and one is a physical way. We talk about models, intensity discrimination, and a little bit about adaptation. And then in the second half we talk about recruitment and compression, because that's the bit that we're obviously most interesting for practical purposes. So first of all, allow me to digress a little bit, talk about definitions here, because there are only 3 real perceptual things that are connected to sound. One is pitch, the second one is loudness, and the third one is I'll let you think about that for a second while I just define the pitch. Pitch is that attribute of the auditory system in terms of sounds can be ordered on a musical scale. So that's a really, really rough definition, and as all of this perceptual definition, most of them, they're very rough. So if you can play music with it, it's got pitch. That's the simple definition of that. Similar with loudness, namely the loudness definition is the attribute of an auditory sensation in terms of which sound can be ordered on a scale from quiet to loud. Now, is that a good definition? is as good as it gets for our purposes, because we find out that loudness is a highly subjective measure, and we cannot easily put a computer in the charge of measuring loudness. We can put a computer into charge of measuring intensity. That's easy because that's a physical definition, but not of loudness. So, physical attributes that mainly influence loudness is sound pressure level. And pitch is frequency. That's right. Anybody came up with the third one?
Time scale.
Quality. Interesting one. I should give a whole lecture on quality. Quality of what?
The waveform.
The waveform. Come on, you can do better than that.
So you're looking at the definition of the waveform.
Quality of speech, I accept. That's a good one. Quality of music is another one that we could talk about. Absolutely. Because the main thing, we actually want to give people, as audiologists, a better quality of life. And how do we do that? Not by making everything audible to them, but by improving the quality of their perception. And the main perception that our people really care about is speech. So that's true. It's a good one. I haven't actually thought about that. There was another one?
Like time scale.
Time scale. How does that work?
Like, presentation period, to get another word.
Yeah. But not very important as such. No. No, you don't measure that really. That's something that is there that you can fight against, but that's not something that you really want to. It's not something that your brain puts a lot of effort into measuring. What does your brain put a lot of effort in? Where does the sound come from? That's what I want to hear. It's localization. That's a real attribute of perception that is well understood, and we have a whole lecture on localization later on. But today we talk about loudness. Next week, 2 weeks, pitch, and then localization. Right, here's the physical range of perceptible sound pressure level. We start, let's look at this graph here on the right. You probably have seen something like that, which makes the connection between the measured sound pressure level in decibel, or here PSI, because it's, I think, American chart. We wouldn't do that because it's not an SI unit. But the decibel is an SI unit. At 0 we have the threshold of hearing. We call that very faint. Moderate sounds, loud sounds, deafening sounds, painful sounds. The whole range goes over 140 decibel, which is, if you plot it as a ratio of numbers, I think 14 orders of magnitude that the auditory system can work with. We never ever go above 120 really, for ethical reasons usually. So that's more a theoretical one. It's also theoretical up there because actually sound becomes a different perception because you start feeling it with other sensory systems. Like your vestibular system, or even just with your stomach, because you start feeling vibration. Now this is we've seen that already, the auditory response area, in terms of sound level, in terms of decibel, as a function of frequency. So we know that loudness depends already not only on the sound pressure level, but we know that sound, well, the perception of sound depends on the frequency as well. So is loudness the same as intensity? No, it is not. Loudness is a perception, and the SPL, the sound pressure level, is physics. If it was a straight line, it was the same. At very high levels, they actually do sort of become the same, because this line is not too far away from, but this is more a theoretical argument here. If you're interested, and you should to some degree, into the physical properties of how we measure sound pressure level and how we measure sound intensity specifically, there's a very good introduction from Brühl and Kier on Blackboard. It's a long document, but the first 3 or 4 pages give a nice connection, or give a nice explanation of what the connection between pressure and intensity is, because it's not trivial. For our purposes here, we talk about pressure because that's what we usually measure, but just be aware that pressure is not the same as intensity, specifically for the reason that intensity has a direction and sound pressure doesn't. Sound pressure is what we measure with our normal microphones, and actually what we measure with our ears as well, and that's good enough for us, but it's not exactly the same as intensity. Okay. How can we predict how loud a sound will be perceived? It depends on the physical characteristics. We need to know something about, well, we do need to know something about the intensity, about the frequency, and other things. Like the duration, for example. Very short sound is very quiet, a bit longer sound is a bit louder. What different sounds appear to be equally loud is interesting for us, and can we construct a scale of loudness? So, here's a little quote, Kurt Tucholsky: "Noise is the noise of others, and one's dog makes no noise." That means, in other words, noise is subjective. We don't really talk about noise as a physical or a psychophysical concept. So there are many kinds of noise, but there's only one silence. I like that one. So one person's noise is some other person's music. And actually that goes quite a far way, because it's been shown, it's been a recent study, you might have heard that on the radio last week, about musicians in the US and the rock musicians and their hearing loss, and it sounds that they ought to have a lot more hearing loss than they actually do have. So even if you're exposed to a lot of loud music, you're not necessarily get a hearing loss from it, because there is some concept of positive noise. So you do have, this is it's not quite understood, but for some people some noises are less effective than other noises. Loudness is a perceptual, subjective characteristic of the sound, as opposed to the sound pressure level. I think that is clear now. Right, equal loudness contours. This is how we measure loudness, physically measure loudness, described in ISO 226, International Standard Organization. It actually has been overhauled, I think, in 1993. Need to check that if this 87 is still the recent one. That's a method of measurement, and that defines the phone. I'm sure everybody has heard of the phone. Phone as a measure of loudness, not of decibel, but it is defined as the decibel of a 1 kilohertz tone that has the same equivalent subjective loudness as any test sound. So we have a test sound that gives you all of that what you want to know. Let's say we want to know how loud this air conditioning up there is in subjective measure, not in SPL. In SPL we would hold a sound level meter and press some buttons and it tells us as 40 decibel. What does it mean? What does it mean subjectively is really difficult to because the only way that we have to actually measure it, well, there are two ways. One we get to later is a clever method, and the phone method is you have to adjust the 1000 hertz tone in the level to be the same loudness as that sound. It's quite difficult, isn't it? And that's the problem. It's difficult, it's subjective, and if you do the experiment 2 times you probably get 2 slightly different results from that. Right, but the phones, if you have simple signals, like in audiometry, it's easy, because everybody is able to compare the loudness of a 1000 hertz tone and a 2000 hertz tone, for example. So these phones are designed to give sound level meter readings a useful interpretation, because the sound level meter is a useful device, presumably, but it measures sound pressure level, and therefore underlies all sorts of restrictions. Namely, the sound level, as we know, the sound pressure level is not what's loudness. Simplest example, if you have a 40 kilohertz very, very loud sound, would you think that's a very loud sound? No, you wouldn't, because you wouldn't even hear it. It's not in our range of hearing. So we need to do something. And the first thing that we need to do is to restrict our measurement to the frequencies that are actually in our auditory range. This is where these weighting curves come from, A, B, and C, and we'll see the A curve in a second. That's the way that is very often is used. An alternative way, and arguably a slightly better way, is to construct a psychological scale, and we'll talk about that in a minute. Okay, first the equal loudness contour. So in terms of frequency, if you have pure tones, say of 100 hertz or 1000 hertz or 10,000 hertz, you can adjust them all subjectively, and that has been done for lots of people, that they all have the same loudness. It's subjective loudness, okay? It's not sound pressure level. The sound pressure level of the same loudness is here. So all of these sounds, so 1000 hertz we know is 40 decibel. That's the definition of it. 40 phone at 1000 hertz is 40 decibel. At, say, 3000 hertz, the sound pressure level actually is equivalent of, I don't know, 35 decibel. Goes a little bit down. And at 100 hertz, it's more like 60 decibel. So you can do that, and you can extend that also to, that has been done, that's what I mean, has been upgraded to different sound levels. You can do that at different sound levels. So these are the ISO intensity curves for all of the perceived loudnesses. Yeah, that's the subjective measure. So here the subjective measure of the threshold is equivalent to our MAF, the auditory field measurement of threshold. It's around 2 phone, 10, 20, 30, 40. Okay, so that's good because that gives us some way of connecting the physics with the loudness. Namely, we can rely on that and say, people in the past have tuned 1000 Hertz tone in the level to something. And we say, this car has, do you get that? This car produces 100 phone loudness. Have you ever read anything in the adverts? No. And the reason why is nobody knows really what it knows. Maybe it should produce something. They still do something like washing machines or dishwashers. If you buy a dishwasher, it always tells you, what does it tell you? dBA, which is connected to the phones, as we see in a second, but it's not as good as a subjective rating would be. An actual subjective rating is I discovered yesterday when I went to Shirley Market. Anybody know Shirley Market? Greatest place in the universe. You get everything, including fireworks. And they actually sell fireworks now with a with a loudness rating. And since I have 2 little kids, I wanted very quiet ones, so you get the loudness rating 1. And that's actually useful. That's more useful than it would say, this is 110 decibels. I mean, most people don't know what that means. But if it says, this is loudness 1 or 2 or 3 or 4, I know exactly what I'm up to, isn't it? So that's useful. That's where this scale comes in. And loudness is a scalable measure that we want to, that is best described by a scale. Okay. But here, if we have these phones, be careful, because it implies that there is a scaling relationship, like 80 decibel, 80 phone would be twice as loud as 40 phone, and that's of course not true. Well, not of course, but this is, as it turns out, not true, and therefore this is like an intermediate step to something more useful, which I define here, which is a zone. You heard of zone? Probably not. Zone is a direct way of estimating loudness. Namely, you would ask, to measure it, you would ask people directly how loud something is. If I had time, maybe at the end of the, I'm not sure how long we actually need today, maybe we have 5 minutes time to do a little experiment. I'll play to you some sounds and you tell me how loud they are. And what people, in an experiment like that, what you would ask is just a number. I find that fascinating in terms of psychophysical experiments, that it works, but it does work, and you don't believe it until you do it yourself. So the rating is, I would just say, now you give me a number, how loud that is for you. And I don't even tell you what the rating should be like, between 0 and 100 or between 0 and 1. You completely make that up yourself. And I give you another tone with a different level, different loudness, and you give me another number, and so on and so on. And that way we create a scaling value, because your subjective scaling, the one thing that it does hold is the relationship between, you would be very good in telling me one sound is twice as loud, perceptually, than a quieter sound. That, it turns out, people are very good at, even if there's nothing physical related to that, but perceptually you know when something is twice as loud. And this twice as loud has been used to define a measure, a subjective measure, which is called the zone. It relates on something which is called Stevens power law. I've got the equation of that in a second, which means that perceptually the loudness doubles every time I go about 10 dB higher up. This is not a firm law, this is a measured law. It's not exactly 10 dB, but this is roughly true. And that leads to our perceived loudness of zone, which is defined as 1 if you have 40 phones. 40 phones you have if you have 1000 Hertz tone of 40 decibel, which we can measure physically, and that is defined as 1 zone. And then if you double the loudness, because of Stevens law we have 10 dB increase, so 50 decibel would be a 2 zone, 60 decibel 4 zone, 78 zone, and then you get a range between, well, this goes lower than 40 obviously, lower than 1, between 0 and about 60 for reasonable sounds. Now, because the zone and the phone are both subjective measure, there is a firm mathematical correlation between them, which is described by the Stevens power law, which is a loudness, which is on the y-axis in here, is a factor times the intensity. This is an I to the power of minus, not minus, but 0.3. That's the Stevens power law. So if for everything above 40 decibel here, 40 phones, I start myself, you've got a linear correlation between those. So every 10 dB roughly, you double the sounds, the perception. So there is a sort of a physical connection between decibel and loudness, but it is not exact, and it certainly doesn't hold for anything below 40 decibel. Because 40 decibel, 40 phones, you have a much increased sensation for the loudness differences in between there. Okay, here's a little overview of how a sound pressure level connects to sounds. So auditory threshold is about 0 decibel, it's about 0 zone, very calm room 0.1, 0.4, and so on. I'll leave that to you to go through that list. But that's a useful subjective measure now. So this gives us the handle of connecting subjective with objective sound pressure levels. Okay. So, a little bit of a summary. Loudness N in zone and loudness level in phone. They're the two words, loudness and loudness level. They're shown here. They're easily converted, but psychoacoustic perceived loudness level and the objectively measured sound pressure level in dBSPL cannot be converted. There's a trick in there, which is the dBA level, but there's no formula to do that. So typical question, how would a 0.5 zone be in decibel, is not answerable. We can only compare them or connect them via a 1 kilohertz pure tone, which is not very user-friendly, if you like. Distinguish carefully when looking at the volume, which is the magnitude of sound, but zone is part of the loudness, phone is part of the loudness level, and avoid the layman's term, well, it's not the intensity, it's not layman's term. If we use it like loudness, it is a well-defined concept if you go into physics, but we're not usually dealing with physics, we're dealing with the perception. dB or dBL, SPL are sound pressure level. dBA is a filtered measurement, and now I show you the dBA filter curve. I'm sure you've seen it. Everybody who has had a sound level meter in their hand know that we usually switch on the dBA setting. Who has ever done that? No, most people. Why do we do that? We always say very arm waving, the A curve is used for noise measurements because it is closely related to the frequency response of the human hearing level. But, and here are a number of buts, in practice I should have put these two figures together. In theory, this curve should look like this curve, this blue curve. Inverted, obviously, because it's a filter. But judge for yourself, this curve has a lot of dips and bumps and everything. The A curve is just a very straightforward filter, which is for technical reasons, because it can be much easier be implemented. But it's not very close to the hearing, to the 40 dB curve. It certainly hasn't got the decrease at between 10 and 20 kilohertz, so there's actually another setting here that should go from straight down, so that the higher frequencies are not overrepresented. And it only really works at 40 decibel tones. 40 decibel noises. This is almost always used for higher levels, which is a purpose it was never intended for and not suited to, and therefore give lower test results than our ears are hearing. So be careful with the dBA. Everybody uses it, but it is important for us masters audiology to understand that it is not really equivalent established to be the best measure for that. In fact, the dB and C curves have been developed for higher sound levels to connect perception with physics. Okay. After I destroy everything that you know now, let's build it up again and talk about how the ear actually does this thing of loudness perception. What is it that makes us perceive a sound as that loud? And the basis for that is a function that I already showed you, the rate level function, which gives us an auditory nerve. So it's a single cell recording from the auditory nerve, gives us a lot of information that we need to know to understand it. So a typical auditory nerve fiber looks like that. If we have a sound level and we go up in decibel and we just count how many spikes per second it fires, then it will have a very low or a medium spontaneous rate here in this case. It will have a threshold, which is between 20 and 30 decibel here, where it starts going up, and then it will saturate. So what does it tell us? If we want to measure loudness, it's a good first indication to say, okay, the more spikes I have in my auditory nerve fiber, the louder something is. Turns out that's probably the best description of loudness, the best model of loudness that we can come up with. But we need a number of other features for that simple model, because obviously, how would you be able to tell, well, how would you measure threshold in this one? And threshold is usually, well, at 1000 Hertz at least, 0 decibel. Well, you can't. You need something better than that to measure something at threshold. And how would you tell the difference between a 60 decibel sound and a 70 decibel sound? You can't, because if you just count the number of spikes, they're both roughly the same, actually even goes down a little bit. So if you just translate that model, you would say the loudest sound that you have is 50 decibel, and then if the sound level goes high, it would actually decrease the amplitude. That's not what we perceive. Okay, so we need one more issue here, solve one more issue. That's called the dynamic range problem. How do we code intensities accurately over 120 decibel if our primary neurons can only have 40 decibel dynamic range? I go back to show you where this 40 decibel comes from. This is the range between here, about 25, to, in this case, well, about 60. Not even 40, it's 30 decibel that this neuron can give us in loudness information. But the answer is, we've got more than one. We've got about 30,000 of these, 30,000 auditory nerve fiber that all carry a little bit of information, and they carry information at different rates. This is another one that I already had up there. Now we understand it maybe a little bit more. Namely, we have auditory nerve fibers that we can discriminate in mainly technically three, but mainly two important groups. Namely, the ones with the high spont rate, which are these ones, that have a very low threshold. They're the ones that work at threshold, and they detect very, very quiet sounds. And we have the ones that have a very high threshold, but also a very high spontaneous activity. So they're less reliable, but they give us a bigger dynamic range. So here's my little figure to hopefully make that a little bit clearer. We've got two different auditory nerve fibers, a blue one and a red one. And this one would be a type 1, so high spont rate, has a high spontaneous rate, and then a low threshold, so it would start pretty early on, but it also then saturates very quickly, whereas the red neuron has a low spontaneous rate and has a high threshold. That has a small dynamic range and has a large dynamic range. So individually these neurons are not very helpful, but if we put them together, we have an enlarged dynamic range. And put 30,000 of these together with very different spontaneous rates and very different thresholds, we have solved the problem. That has been shown that this actually is a viable model, that we can cope with a dynamic range of 120 decibel by putting together lots of these neurons. But connecting that now to something completely different, namely the input-output function of the basilar membrane. This is a picture that you have seen already as well, and I want to connect these two now. Namely, if you put a sound pressure level between 0 and 100 here, say, on the basilar membrane, and we measure the relative basilar membrane response, which is not sound, it's measured in decibel, but it's just like the amplitude. Let's say the amplitude of If we have don't put in the dead one. The dead one here, as you remember, is a straight line with the function of 1. So if we put 40 decibel in, we get 40 decibel out. In the normal basilar membrane, we don't have that. We shift the low amplitudes upwards, but the very high amplitudes are still about the same level. So for a normal person, the response of the basilar membrane at 0 decibel is already pretty high. That's how we hear it, and this is then compressing the dynamic range into a useful measure. So this is a little figure from Brian Moore's book. I try to talk you through that because that connects exactly the physiology with the perception. So these are input, or the input-output, the rate level functions of 3 different neurons. And neurons are pretty blind to their input. They don't differentiate. They're the same neurons. If you have a low threshold or a high threshold, they don't really care. They only care about their input, but they're the same neurons. That's why these actually look pretty similar. So what we see here is the relative response and the response in spikes per second. So this one would be exactly the figure that I had before, turned on its head. So we've got here a high spond rate with a low threshold and a low spond rate with a very high threshold. But they all look pretty much identical in terms of their rate level function if we talk about their relative response. Now if we put them together with our function of the basilar membrane, because of the outer hair cells that come of course into the play here as well, the outer hair cells increase the amplitude for loud sound, for quiet sounds, but they do not increase the amplitude of loud sounds. So they are responsible for this function of the basilar membrane, of this compression, and our neurons' responses then become exactly like the ones that we see at. So as a function of input level, we've got the high spond rate that go up sharply and the low spond rate that go up very, very gradually. So that explains about everything that we observe in terms of the physiology. Just going back, this is just one of the examples, but we know from measurement, hundreds of them, that we've got these we've got a continuum of neurons that go in between these two examples, these extremes, so the very sharp ones and the very steep one. And together, physiology tells us measuring the number of spikes of all of these is quite a good model of the predicting the loudness, the subjective loudness. So, there's a little formalization of that, and Brian Moore has done that, as he did most things, namely, I summarize it here. The number of active neurons is approximately the loudness. If you do it a little bit more in a mathematical way, why do we want to do that? Because it's useful, because what we actually would like to have is a sound level meter that measures loudness and not sound pressure level, wouldn't we? I'm not sure why you can't actually buy these things, but there are quite good models now. And in theory, I predict that you could probably, produce one certainly. Unfortunately, you can't buy it, but it would be useful to have a measurement device that you put into a room and it tells you, yeah, this is a 30 sohm background noise and not a 60 decibel background noise, because the 60 decibel don't mean anything. The 30 sohm mean a lot. Okay, so what do these loudness models do? How do they work? Well, they filter the sound first for the transfer functions of the outer and middle ear. Why is that? That gets rid of the 20 kilohertz high frequency and 20 hertz low frequency, so it effectively filters for the dBA curve. So frequencies that we don't hear do not contribute to loudness. Secondly, we transform the spectrum into excitation patterns. Go back last lecture, excitation pattern is what the basilar membrane looks like, the basilar membrane response. And obviously the more the basilar membrane is excited, the more neuron response. And that's the third step, transform excitation to specific loudness. And that is the same as calculate the area under specific loudness patterns, because all of the neurons that are active on the basilar membrane, you can calculate that just by integrating, counting the area underneath the curves. So these are, for example, here 2 bands of noise. which have different bandwidth, but they have the same overall level, so the physical level is the same. They say they have 65 decibel, but do they sound the same loudness? Go back to the what was this called? When we did the experiment where we increased the width of the band, they all had the same overall sound pressure level, but they increased in amplitude, in loudness, unto a certain point where we came to the critical bands. Remember that? That's exactly reflected in here. So we have a narrow band noise and a wide band noise, and if we plot the excitation pattern on the basilar membrane and we integrate the area underneath, we get a good level of loudness. So that's the best that we could come up with, or that we can come up with now in 2014, to actually predict how loud subjectively something will sound to somebody. And there are attempts to use this also for useful things like fitting hearing aids, for example. But these attempts are still in their infancy, and the main reason for that is that this is not easy, obviously, nothing is easy, and takes a bit of time, whereas hearing aids these days are not that powerful. They can't really do that quite well yet. But hold your breath. I think there will be something coming out of investigations like that about loudness that actually helps. Okay. We need to talk a little bit about intensity discrimination while we're at intensity. Namely, how much do we need to increase or decrease the intensity of a sound for it to be perceived as different? And there are two ways, or a number of ways of doing that. One is modulation detection. One is called the AB paradigm. So modulation detection is just you modulate the envelope of a sound. So it's go woo, 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 woo. Do you hear the modulation or not? It gives you an answer if in the signal detection theory, you can define that very well, what the threshold of this perception is, and that gives you a discrimination threshold, a just noticeable difference. Both of these paradigms have slightly different results, and there is a very good program which is on Blackboard. I think it's installed now, not I think, it's definitely installed on all of the lab machines as well. And I invite you to have a look at that to measure your own intensity differences, IL, intensity level test, for a number of frequencies, 1000 Hertz, 2000 Hertz or something, and you can add different levels, 20 decibel, 40, 60 decibel or something. And it's a really interesting experiment, and there are two ways of doing that, these two. In terms of what you get out, well, what you should get out is something like that. If you do it with lots of people that are highly trained, which you're not, therefore individual results always differ. So, but what we expect to get out of that is, if we're completely naive, we would assume something which is called the Weber fraction, because it holds in almost every other sensory system, namely that the relationship of the change of something divided by the absolute value should be about constant. That is true for things like perception of light or brightness, or the perception of weight, or the perception of smell, or anything. All the sensory, this is something that unifies all sensory systems. And we would expect that to be true in the auditory system as well. That means that the JND is a constant value in decibel, because we divide. Decibel is a dividing measure, independent of level. But the auditory system is tricking us, because it's not quite true. What we get is what's called the near miss to the Weber law, perceptually. And here's just one figure that illustrates that. If we, for wideband noises, above a certain level, about 30 decibels, so below that is very quiet, weird things happen, but above that it is roughly true. Roughly true means these white dots are about the same, aren't they? That's about right. And that means that over about 30 decibel you have a discrimination level of about 1 decibel. That's the take home. If you take one number away from this lecture today, then it is that 1 decibel. You're able to discriminate two complex sounds if they're 1 decibel apart. So if anybody tells you ever with a paper that they increase the loudness on 0.5 decibel, you can throw that in the bin immediately because it's actually below the threshold of perception. So this is a nice round number, and I believe in retrospect, not quite sure, but that's the actual reason why we use decibel, because and not bell, because bell is the actual value that we calculate, but decibel is a tenth of a bell. But 1 decibel is about the unit of hearing, if you like, the unit of sound perception, because it is the smallest difference that we can perceive. Now for tones, the whole thing breaks apart a little bit, because it actually isn't constant anywhere. It just carries on decreasing. So the louder a sound is, the better your discrimination. Starts at 1.5 decibel, goes down to 0.3 decibel for pure tones. The reason for that is that the auditory filters. Everything has to do with auditory filters. And in this case, the wideband noise covers all the auditory filters at the same time. But one pure tone only ever one auditory filter. And if you go, well, it doesn't. If you go higher in amplitude, going here to the right, you actually use filters from nearby areas, because you become so loud that your excitation pattern crosses over in other bands, and the other bands can make use of that information as well. This is a trick that the auditory system uses that we will encounter later on. Here it's good, but usually it's bad. You know the term that is used if you use filters from next door? You recruit these filters for your own purpose. That is recruitment. And you know recruitment as something completely different, but recruitment is a big term. It effectively only means recruiting other filters for the work that you want to do. Okay. But now to something completely different. There's some interesting things that happen if you listen to sound of a loud sound over a longer time, namely adaptation. Something isn't that well known, but adaptation happens everywhere in every sensory system. Remember my probably very first lecture, I always argue that for the auditory system it doesn't really matter what is there unless it changes. So the changes are the ones that the auditory system is interested in. And here as well, here's experimental evidence for that. And you can argue to which degree this is normal and where it becomes critical. What's the word? When hair cells get damaged and it becomes clinical. But there is a continuum between we always adapt to something and we don't listen to it anymore. That doesn't mean there's anything wrong with you, yeah? But if it's something is too loud and you hear it for too long, it also increases. So here's the one experiment. Let's talk about this 1000 Hertz tone. You listen to a 20 decibel 1000 Hertz tone for how long? 3 minutes. And then you switch it off. And then you listen to it again and you make a little experiment how good your discrimination threshold is. And we already set the discrimination threshold here is, well, in this case, I don't know where it was exactly, but it would be about 1 decibel, yeah? Roughly 1 decibel. But you find that this is actually increased in some cases. So you're listening for 3 minutes to a sound, increases your threshold of discrimination. You get worse at discrimination, usually. Why is that? Something happens, I don't actually know why it is, but this is just observational, that something in the auditory system gets so used to the stimulus that you get worse at discriminating it. Maybe it's because it's boring, maybe because the signal doesn't actually carry any information, and therefore the auditory system concentrates on more interesting factors in the sound. But this is what's observable over all of the ranges, but very loud sound, 100 decibel, actually has quite a large effect. But even more interesting in here is that if you do that experiment, 1000 Hertz tone, and you measure the 1400 Hertz tone discrimination level, it goes up even more. Now remember last lecture, 2 lectures ago, why is that? upward spread of masking, because the 1000 Hertz tone affects itself, but it even more affects higher frequencies. So they get masked even more. The same is visible in that experiment, which is the recovery over time. So here's just a snapshot after 3 minutes. Here is the time after in minutes after that sound. I don't know if it's the same experiment. Yeah, it was 3 minutes, but it was 120 decibel sound. So it's a very loud sound you listen to for 3 minutes. You would certainly not get ethical approval for doing that experiment these days anymore. So therefore these are always from the 50s, these experiments. I honestly don't think it would do much damage, but you still wouldn't get ethical approval for these anymore. So we have to rely on data from the 50s. So you play 120 Hertz tone at 500 Hertz, so very low frequency, and all of the upward spread of masking means you have all of the higher frequencies affected by that. And you measure again the threshold elevation. And the threshold elevation after the 3 minutes for a 4000 Hertz tone has this curious curve. It's completely not quite clear why that is the case. I mean, it goes go up 1000 Hertz, 4000 Hertz. The difference here is a wide band noise and a narrow band noise. That doesn't matter that much. Let's just concentrate on that one here because it's the nicest shape. You see that these threshold curves go down and then up again. So there are a number of different, obviously a number of different mechanisms that work to make this threshold shift happen. So the first observation is even after 10 minutes it doesn't go down to 0, which means after 120 Hertz tone you have a prolonged damage of something. Well, call it damage. It might be an adaptation, but it might well be a damage. And if it never goes down to 0, you would have a permanent damage. But there are a number of repair mechanisms and damage mechanisms in the first few minutes. With today's knowledge, we know that at least one of these, well, I mean, we understand a number of these. One is the depletion of potassium, which leads to short-term adaptation. That leads to the shift up here. That is replenished pretty quickly, but it does go up again. And I don't really understand why it goes up again. Neither does anybody, as far as I'm aware. But my best guess is that there's something to do with the tipplings that are actually affected from the outer hair cells. So tipplings, remember that? They are the ones that actually open the gates, and they're the most sensitive part in a mechanical way that can happen, that can be damaged. 120 decibel is loud, but not that loud. It doesn't affect the hair cells. It doesn't rip out the stereocilia, but it does affect the stipplings, and they get damaged, but they get repaired as well over the time course of minutes. But then it becomes hours, and I think something like 18 hours or something has been measured as the longest that it actually takes to recover back to normal again after loud sound exposure. Okay, so it's a little summary. The magnitude of the vibration of the basilar membrane at the peak of the traveling wave increases with increasing level. Yeah, excitation pattern becomes higher. It displays our compressive nonlinear growth. That is the function that I always plot. So you've got the shift at the bottom, and then you go in a compressive growth. There is an associate with increase of rate of action potential in nearby auditory nerve fibers. And we have the dynamic range problem, which we explain by the simple model that we measure the excitation pattern, or in other words, the number of neurons that are active for any kind of sound. This is what we perceive of the loudness. And the magnitude of the vibration along the length of the basilar membrane also increases. And there the growth of the high frequency more rapid at the peak. That means every sound of a very loud sound affects rather all the frequencies to a higher range than itself. That is the upward spread of masking. Here's the leading question. Can you see how that is connected to upward spread of masking? Yes, we can. That is upward spread of masking. And the loudness relates to the total activity within the auditory nerve. Nice. That gives me a nice opportunity for a break. before we delve into recruitment and compression. Shall we meet at 5 to 12 again? Because then the next hour will be probably a little bit longer. Yeah? Yes.
Because I need to have a chance of actually understanding the original paper, but yes, it would be quite a difficult situation. But I will try to give you constructive feedback.
Thank you. How long will it take us?
So you like, is it different in all between the what's your favorite topic? What is this? Is this related to what? I don't see how this works in the job. It says 8 to 8. So what do you do with your job? What do you do? You do PTA. Oh yeah, that was those you would tell me today
Yes, I am. Please tell me every time. It shall never happen again. I still need to get back and do last week. I am forced. Actually, let it run. Just to be on the safe side. Yeah, what the difficult bit is when you try to repeat a lecture, it's psychology, because I don't know if you ever tried it, but talking to your computer for 2 hours without anybody listening is a really frustrating and disheartening experience. So my suggestion maybe, if you want me to repeat the Panopto recording of last week's lecture, I do it if I get at least 3 of you listening to me. Okay, and then we make a 2-hour slot when we repeat the whole thing. I'm open to that, yes, but it is just so much easier to talk to somebody rather than this stupid computer screen. Say again? That's what I mean. That was So organize yourself. If you get 4 people or 3 people together in the time slot of 2 hours, I'm free for the rest of. Well, I'll make time for that. Okay. Okay. Let's carry on. Types of hearing loss. Why do I say that? Because different hearing loss, especially conductive hearing loss and sensorineural hearing loss, have a different effect on the perception of loudness. The conductive hearing loss is frequency dependent, but linear acoustical attenuation, which means the conductive hearing loss comes from a transmission problem. It does affect the amplitudes, but it's linear. It doesn't create new frequencies. Sensorineural hearing loss is more difficult, as a normal thing, obviously, that affects us with the loudness perception. And we have a summary there. We have the cochlear hearing loss, we have the neural hearing loss, we have the strial hearing loss, and we need to understand that. What's the problem? Linking to last week's lecture, here's our well-known, now we choose to plot it as velocity as a function of sound pressure level, and before curve here is just one curve of the basilar membrane. That's the curve that I'll always show you, my favorite figure. But if we put, in this case, furosemide intravenous into that animal, the curve becomes much reduced, and then after a while it goes back to normal. So that's just the effect of insult, and I want to make sure, I'm sure you already have seen that a few times. So we lose our compression before we gain it back. But the effect of insult on the basilar membrane mainly affects the outer hair cells, and it affects this transmission curve. So how the basilar membrane responds in response to a sound. Okay, perceptionally now, perception of loudness. What does this insult do to our loudness perception? Here's a very seminal paper, Moore Glasberg, 97. I should put that on Blackboard, by the way. They use subjects with unilateral cochlear hearing loss. Unilateral cochlear hearing loss, they only have it on one ear. You don't find them very often, and if you find them, alarm bells should go off. But because there's this quite often the sign of deeper lying problems that actually don't have anything to do with the ears, but maybe with the neuroma, for example. But if you find somebody and let's say they're healthy, they're good subjects, because what you can do is you can compare in the same person. So with the same ROC curve, you can compare a healthy ear with an unhealthy ear. And in our case, what we want to compare here is the loudness perception of these two. The stimulus that we use here, or the method, is called alternate interoral loudness balance, similar to an old clinical test, probably never heard of. Audio balance, AB loudness balance, so A tone, B tone. But what we're doing is play a 1000 Hertz tone on the healthy ear at say 40 decibel, and then let the person adjust the level of the left ear, of the impaired ear, until they sound the same loudness to them. You're very good in this task usually, about 1 decibel as we know now. You can do that, and you can do it at all frequencies. And what you get out of that are curves like that. So you have the level, let's start with the level in the normal ear. If this is the level impaired ear. If you're normal, you obviously have this straight line. 20 decibel in your right ear probably is 20 decibel in your left ear. This cross here is the threshold. So about 35 decibel, you start hearing it for the first time in the impaired ear. That's just one subject. Yeah? There's average curves, but they look quite similar. Now, if you make that sound louder in the normal ear, you get a very rapid growth of the loudness perception. That's what I always said, until they meet up again at about 100 decibel. Yeah? Textbook, well, obviously that is textbook response at a very low frequency. At 1000 Hertz, this person produces something slightly different, has a slightly less threshold, and produces something that doesn't actually reach up to the 1000 Hertz. So there are subjective differences here. Sometimes they don't go up to the full height, which means that probably on top of the outer hair cell loss here is an inner hair cell loss as well connected to that. At 4000 Hertz, this is even more pronounced. You've got an almost linear growth at 4000 Hertz, but it only starts at about 80 decibel threshold. Obviously, severe hearing loss means there's virtually no outer hair cell left, and probably not many inner hair cells either. Now, interesting, if you do that with a broadband noise person, you get a slightly different picture, because you get a threshold here 60 decibel, but it actually crosses that line. So for that poor person, what's the dynamic range of perception? For the perception on the normal ear here is 40 to 100, so that's about 60 decibel level, is reduced to this person 60 to 80, well 65 to 80, so about 10, let's say just for the sake 10 decibels, so 60 decibel loudness range, which is all the range between quiet and very loud. He has only got 10 decibel left to reduce, to put all of that. And this is what's typically called recruitment. Yeah, you know that from practice. If you tell people that the standard is, the textbook example for that is you have an elderly gentleman and you talk to them and they don't respond. You try it a little bit louder and they don't respond, and you try it a little bit louder and suddenly they say, "Don't shout at me." And that poor guy cannot help himself or herself, because that's the recruitment effect of it. They don't hear anything for all of that, and then you increase it a little bit and suddenly it's too loud. It's actually uncomfortable loud after a short, small increase. So why is that, and where does it come from? Now, there are three theories of loudness recruitment. Actually, two main theories that I will go into. Here's a paper that I put on Blackboard, very recent paper. It's a bit of a review, two pages short paper. This is new in the lecture, in the slide. This is what I only put on over the weekend. So. Apologies if you haven't printed it out at the moment. The first theory that is generally mostly reported in textbooks is this theory A. Namely, these are the normal people. Normal person, remember this is the sound level rate, so the spike rate as a function of sound pressure level. We've seen this function a couple of times, so we have a spontaneous activity, small dynamic range, and then a saturation up here. We have a normal people, normal auditory filter shapes. Yeah, it's a bit schematic here, but it works. And we have a different kind of auditory nerve fibers, low spond rate and high spond rate, with high threshold and low threshold. And each of these features give rise to one of the theories what can go wrong. First is the loss of the basilar membrane compression. That's the main theory that most people believe, let's put it like that. Which means for our traumated cochlea, this curve shifts to the right and becomes steeper, because the outer hair cells don't work anymore, so the threshold goes up, and the working point of this neuron, it keeps its bond rate, but it only starts firing at much higher sound levels. So if you've got lots of these neurons now, you get nothing of the neurons that are still at the low thresholds, but only at the high thresholds, and that explains nicely the steep range, the steep rise of loudness at the higher sound levels. That doesn't explain the recruitment, though the overcompensation, though. That only explains why it goes steeper. So the traditional way, where the word recruitment actually comes from, is from the view of the theory B here, namely the increase in spread. So for the normal people, we have the normal 3 auditory filters, and if we have that frequency here and we make a sound louder, it takes us a while to cross the bands to the left and the right. So at the very low thresholds, we only work in one auditory filter. If we make it louder, we cross over to the left and the right auditory filter. Yeah? That's normal. Everybody has that because our filters are not very steep. That will happen after a while. The point is, if you have filters that are broader and higher, but mainly the point here is that they're broader, is that you don't have to go very much higher to recruit the other filters left and right. That's where the term recruitment comes from, and that would explain why not only, well, probably it's a mixture, it's always a mixture of all of these. This explains why the threshold is higher and why it goes steeper, and this explains why it then can go over the goal, namely you recruit too many auditory filters, and your auditory system or your perception tells you, there's a sound in that auditory filter, and a sound in that auditory filter, and in that one, it must be too loud. There's a bit of arm waving, but I haven't come up with anything better than that. So the auditory system is clever because it does, even if one auditory filter doesn't work, it can recruit, it can use the adjacent auditory filters to make sense of the information. But in terms of loudness, that means loudness is connected to the numbers of neurons that are excited. So if I recruit all the ones from the left and the right, I get too many neurons active, and it becomes too loud too quickly. C here is a bit of a mixture, and it uses this concept of the spontaneous rate, or the different that I went here, so the low spont rate and high spont rate. And the theory here is that we lose specific kinds of neurons first, namely the ones with the high spont rate, low threshold. That's the concept where it has been connected to the hidden hearing loss recently. So that's the buzzword of the decade at the moment. For the last 3 or 4 years, hidden hearing loss. You only lose a specific kind of neurons with the hearing loss, namely the neurons with the high spontaneous rate with a low threshold. Because I'm not quite sure why that is the case, but they are selectively at the bottom of the hair cells, and maybe this is where the damage is most pronounced, and they will go first. So you're left with the neurons with the higher threshold, which has the same effect as the one on top, but you lose specifically the ones with that have a low threshold, and they have other advantages as well because of the temporal processing, and you have a very a mixture then of hearing losses, or of effects from that. Okay, little summary. Cochlear hearing loss is typically associated with a reduced dynamic range, with the loudness of high intensity sounds similar to the normal hearing person, and a loudness recruitment, which means you have a much less dynamic range. You only start hearing at 60 decibel and it's already too loud at 80 decibel. The neural hearing loss means you typically have less loudness recruitment, sometimes more. And it varies between people. That's a take-home message. it depends on the very specific hearing loss. It depends on the frequencies of your hearing loss, obviously because of the filter shapes. It depends if you have dead regions or a neural loss or a cochlear loss. All of that interferes with the perception, and there is no simple way of predicting for a specific person what their recruitment actually looks like unless you know exactly what hair cells are still there and what neurons are attached to them. And there's no way for us of knowing that. Not yet, at least. There's a call at the moment from the EPSSC, the Engineering and Science Council, and they spend at the moment a few £1 million of encouraging people to research exactly that. How can we come up with a better measure of this hidden hearing loss, of the connection between the low spond rate, high spond rate? How do we measure that? Because if we knew what hair cells are exactly, and not only what hair cells, but what neurons attached to the hair cells are selectively, individually damaged, we had a much better way, potentially, of producing hearing aids that help them. Because our hearing aids might be just too broad a shot, because they don't do very much. Come to that in a second.
Sorry.
Yeah.
There isn't any relationship between recruitment and the damage of inner hair cell. Have you ever? I've heard that in the physiology of the inner hair cell, at the loud sound in a normal basilar membrane, at the loud sound, the stereocilia on the inner hair cell move backwards in order to suppress the sound. But in a damaged football, because the inner hair cell has been damaged as well, there is no this backward movement in the stereocilia of the inner hair cell. So this is another theory. I've heard that this is another theory behind the recruitment.
There are a number of theories behind that. I mean,
No
I gave
idea about this?
3. No, I've not heard of that one. Yeah, if you have the paper, I'm happy to have a look at that. But my last sentence here is not 100% clear what the mechanism for that is. There are a number of contenders. The problem is we can't look into the situation, and there's a mixture. That's for sure. It's a mixture of inner hair cell damage, outer hair cell damage, and neural damage, which is the attachment of the auditory nerve fibers to the inner hair cells mainly. So if the inner hair cells are damaged, can mean that the inner hair cells are damaged, or the nerves on the inner hair cells are damaged, but that's certainly a factor, very much so. Okay, what do we do about that now? What are we doing about it now? And here I explain now, the next 10 minutes, what compression actually is, and how we can make use of it for hearing aids in order to restore some of that functionality that we lost. So here's our favorite curve again. I'm sure we've internalized that now. And I wanted to try something which didn't work on my computer, namely give you a demonstration of what hearing loss actually sounds, and this is quite a nice web page for that. It might not work. Should have tried it in the break. So here's a normal hearing person. No. Sorry about that. Try to find a different web page. There are a few, but this is the best one that I see. That can actually that simulates that recruitment or this dynamic range problem and resynthesizes the sound and makes the sound audible as if it was presented to a normal a hearing impaired person. Okay, experiment failed. Let's go back to that. What is compression? Compression provides nonlinear amplification. This curve is a compression curve because it compresses the range from 0, which is down here, to 100 into 50 to 100. That's what the auditory system wants to do. It works by sensing the input level and then adjusting the gain. That's the very short words what the outer hair cell do. They sense the input level and then put some gain on it, namely for very quiet sounds, a lot of gain, and for anything above 50-60 decibel, no gain at all. Very non-linear. Now, how fast should that work? How much do we want to compress, or how much do auditory nerve fibers compress and hair cells, and where should it be applied? These are the questions that I want to answer, and I wanted to turn the question around now because we know the problem. Well, let's assume we know the problem. What can we do technically to reverse it? and we get to something which is called wideband compression, that you probably have heard from hearing aids, and explain briefly what that actually means here, and what kind of compression types we use, namely fast, where there's slow, wide dynamic range, where there's linear and output limiting, and wideband, where there's multiband. So here's a little introduction of what compression means. Now this isn't in your printout again. This comes from a little handbook, the compression handbook from Starkey, which I put up on Blackboard, which I highly recommend reading because it's very straightforward and a language that is very easy to understand, and it gives a very nice visualization of many of the issues. It goes way beyond the scope of this lecture, because it's actually aimed at hearing aid technicians that set hearing aids in the right way. But let me introduce the key concepts here. So, and we go in the lecture after Christmas a little bit more into detail what the details of that actually are. But here is just the fundamentals and the physics behind it. So this would be a normal hearing person, and the colors are not ideal here, but it has three ranges, namely weak sound, moderate and intense sound. The weak sounds are raindrops, for example. Moderate sounds, a person talking. Intense sound is a fireworks. But you'd laugh, actually you don't get these fireworks anymore. It's a thing of the past, is it? I mean, I certainly, not that I want them, but when I was little I wanted them, and then there was no problems to get them anywhere. But now you get fireworks that are actually quite quiet. The loudest fireworks that I come up with are these whee! They're annoying, but not really loud. But I don't know. Right, this is a normal person, and this is the dynamic range of this normal person. So it starts at very quiet, and it goes maybe up to extreme loud, and the blue range is the range of hearing, the dynamic range of hearing, where we want to hear. So this is what we want to achieve. We want to hear everything from very quiet, well, too soft, to hopefully not too loud. But if we have a hearing impaired person, sensorineural hearing loss, this blue line, compare this one, the dynamic range is compressed, is reduced. So they still hear the loud sounds and the moderate sounds, but they just simply don't hear the weak sounds. So what can we do to compensate that? Well, first of all, we could just amplify the sound. Now, 100 years of hearing aid technologies in 2 minutes, why don't we just amplify sound? Amplified sound means we put an amplifier in your ear, and this is what every hearing aid did till, I don't know, 1990? Don't know, before your time probably, or maybe even 2000, something like that. They were linear amplifiers, maybe with a limiter at the top, and it turns out they're actually really good hearing aids. I'm not going into detail with that, but there's a lot of things going around in the hearing aid technology. But it turns out that most people, if you give them the choice between a linear amplifier and a £4,000 Siemens hearing aid, most people actually prefer the linear amplifier because it sounds better. So there's a real question of whether you want to spend £4,000 on a hearing aid. But there are other issues. But let's answer the question first, why not just linear amplifier? And there's one reason, because if you make it too loud, it becomes uncomfortable, and if you limit the output of the device, because it cannot go above a certain limit, let's say 120 decibel is usually the limit. I think they're high-powered hearing aids now that can go up to 140 decibel, but for normal hearing losses, 120 decibel is about acceptable, and then you run into the problem of clipping. As simple as that, you just distort the sound. So there's two problems with linear amplification. You either it would get uncomfortable out. So what does actually linear amplification means? It means you always put 60 decibel gain on the sound. So very quiet sounds becomes nice and comfortable, but a loud sound becomes uncomfortable. That you don't want. So you need a limiter. So the bottom figure shows what the limiter would look like. So loud sound, you can just clip it. But what does the clipping do? It reduces the quality. It brings in distortions to the signal that are unacceptable. That if you listen to them, it sounds horrible. That's why people don't want that. So linear amplification is good for a certain range of sounds, but not good enough for louder sounds. So we need something better than that. So here's my figure. These are the two figures at the top that we already had. So the normal person and the hearing impaired person, sensorineural hearing loss. If we just have a linear amplification, it means we change we just make these louder. We make the quiet sounds louder and bring them into the range of the person. But then the too loud sounds become uncomfortably loud. So here's the limitation of that. And that's why today's hearing losses, hearing aids, do something more than that. They amplify the quiet sounds to get them in range, but then they compress the range of sounds. So they make the quiet sounds louder and the loud sounds quieter. That gives us the range of hearing, or the range of sounds, compresses into the limited range of the dynamic range that the hearing impaired person still has. Okay, but how do we do that? What are the characteristics of that? We need to learn to read these compression charts. I'm sure most of you have probably seen them a lot of times. Namely, this is the output as a function of the input of one of these, and I'll just show one of these bands. And this is just to show the definitions of what these compressors, how they're defined. So we amplify all the quiet sounds. So 20 decibel sound becomes 50, and this is linear. 30 becomes 60, 40 becomes 70, 50 becomes 80. That's fine. That's linear amplification. It's great. Everybody loves linear amplification because it doesn't distort sounds. But we cannot carry on with that blue line because otherwise we go into uncomfortable levels. So we put a point in here which is called the compression threshold, CT, at which we kink this curve and we compress the sound levels above that certain level. So we need two values to define the compression, namely the compression threshold and the compression ratio. Here's a definition of the compression ratio. If it's linear, we've got 1 to 1, which means if we put 10 decibel in, we get 10 decibel out. Here it's 2 to 1. If we get if we put 20 decibel in, we get 10 decibel out. Okay, it's just to breeze through all of these. And what I like is this compression picture. This is what we can do. A is this gondolier with a hat on in a normal situation. The level of the water is the amplitude of the sound, and the hat or the door is the maximum uncomfortable level. If he hits his head, he's suffering, so he doesn't want to hit the head. So this person goes through smoothly, but if you make the sound too loud, linear amplification, loses his head. That's not good. So what does he do? Kinks his head forward. That's one solution. Or bends his upper body forwards. Which is better? Well, probably a mixture of both. But this version number D here, where you bend the body, is preferable because you have
Less distortion.
you have less distortion. No, not necessarily. You have distortions, but you have a wider range of which you can do that because your head can only go that far down. If you raise the water level again, then your head doesn't help. So obviously the level of the kinking is the ratio, and where you tilt is the threshold of compression. Okay, that's a nice figure to visualize that. Here's a little bit of random information for you for your next pub quiz. In fact, we all suffer from the recruitment of the compression at the low frequencies. Just want to make clear that this is not something that is actually unusual. This is used in an everyday situation, as I show you in a minute, but it's also distracting for a number of purposes, namely going back to our phone curve. So here's the 40 decibel or 40 phone curve. Perception of that. If you have quiet sound on, say, a CD player or a car radio, and you increase linearly the volume, which is what an amplifier does, imagine what will happen to this 40 decibel or 40 phone curve. If you push that upwards, you get at low amplitudes, you go above the level of this 100 phone curve. Yeah. This is an effect of our compression, our recruitment at low frequencies. Here we have a much lower dynamic range than we have at 1000 Hertz, 2000. Our maximum dynamic range is, not by coincidence, about 2-3 kilohertz. At low amplitudes, at low frequencies, we all suffer from a compression, which means if we linearly amplify everything, we get distortions for us, for our normal. That's why good amplifiers compensate for that. Well, good amplifiers, there's a whole research, there's a whole industry around how you build good amplifiers, but it's not just the case of amplifying everything linearly. You need to take care for the perceptual idiosyncrasies of humans. Okay, here's another fun fact where we see compression at work, which is called the loudness war. Namely, normal compression in the ear is useful and necessary because we need to compress the 120 decibel into the 30 decibel of the neuron. That's why we have compression. If we had electronic built things in our brain, like transistors, and a much wider dynamic range, we wouldn't need to talk about that. But because neurons are inherently restricted by nature, we need to compress it down to their level. But here's an interesting one. In audio, compression can be used to make sounds louder. How does that work? You compress something and it becomes louder? That's a bit contra-intuitive, but it's exactly what happens if you compress sound. Namely, here are two recordings from Michael Jackson, black or white. First one you can't read that. 1991, 1995 and 2007. You see the difference between these? The same song. It's just mixed differently. Now what happens is that people put more compression into the sound, which means they reduce the dynamic range. They put, here we have a larger dynamic range. So you've got areas, lots of areas with quiet sound, then medium sound, and then a few with very loud sound. Compared with here, we've either got loud sound, here we've got one break, and then we've got extreme loud sound all the time. So they make everything about the same loudness, namely the loudest loudness that you can make. Why do they do that? Good question. Google it, or Wikipedia, the loudness war. Because over the last 20 years our perception of music has changed, and what we perceive now as a normal song 20 years ago would have been much too loud, and 20 years ago what we would have perceived as a normal song would now sound slightly old and not loud enough, apparently. So here's a useful application of compression. Exactly the opposite of what a hearing aid. Sorry, this is exactly what the hearing aid does. The hearing aid. This is a hearing aid, effectively. They put Michael Jackson through a hearing aid because they up the lower ones and they reduce the top ones, and everything becomes equally loud. Yeah. Okay. So there's a number of questions now how we need to deal with that compression. First is how fast we have to do that. Because we're talking about a constant stream of sound over time, and what we need to answer is what our electronics in the hearing aid needs to do with that, because it needs to first measure the sound and then do something with the sound, namely up the loudness or down the loudness. But how should it do that in a millisecond or a second or a minute? If we want to simulate what the basilar membrane is doing, we would need an instantaneous compression. What the basilar membrane does in the outer hair cells is on a cycle by cycle, which is essentially instantaneous. So every cycle is compressed exactly at the right moment. We find out in a second why we don't want to do that. The auditory system does know about this acting compression. That's the problem here. If we had, well, what would happen? Question yourself, what would happen if we did exactly that? Namely, take every millisecond of sound and then put maximum compression to it. We would actually end up with Michael Jackson here, even worse. Because every aspect, every millisecond, if it's quiet, we increase the loudness a lot. If it's louder, we don't do very much. So in the end, it would all be the same loudness. We wouldn't have much dynamic range left. And that's no good. That would perceptually be really, really rubbish. But the basilar membrane is doing pretty much exactly that. It reduces the dynamic range by compression, always to the minimum that the auditory nerve fibers can do, 30 decibel or something. But my point is, the difference between a hearing aid and our basilar membrane is that we know what the basilar membrane is doing. I say we as our brain, because we control it. So we have a control gauge somewhere in our brain that knows, at this moment we imply that much compression. And we can compensate for that. And perceptually, for us it's fine. In a hearing aid, I can't do that. If my hearing aid at every time instant uses maximum compression, it would sound horrible to me, because I can't compensate for that knowledge, especially if the compression changes all the time. So what are the options for our compression? We can do it near instantaneously. That would mean if I shut the door, it would have exactly the same amplitude as if I was doing that, which you don't want. You want differences. You want a dynamic range difference. We could do it in tens of milliseconds, compensate for variation in the phoneme or syllable level. That's obviously interesting for speech. We could do it in the hundreds of milliseconds, compensate for variations in word level, or we could do it seconds level, or even longer than seconds, compensate for variation in level due to changes in the environment. If we do that, we approach something which is called the automatic gain control, which just means that we take the environment and subtract it from our perception, which is nice and which is done in all hearing aids because they always should have operating at about the same sound level. Compression comes at a cost, which depends on speed among other parameters. What is that cost? I haven't spelled it out yet, but why? Actually, I think I did spell it out. What's the problem with compression? Why is it not easy? We just use the person with the head and compress everything, and everybody is everything is hunky-dory. What's the main problem?
Hearing aid?
Yeah, with the hearing aid, or with Michael Jackson, doesn't matter. Michael Jackson in itself is a problem, I suppose, but for a hearing aid, it's the quality. If we compress too much, we get quality issues. If you do it too much, it starts. If you do it too fast, that's for sure, it starts sounding rubbish. And if you have a too low knee point or a threshold point, it starts sounding rubbish. Everything, going back 2 lectures ago, everything that is non-linear will introduce distortions into the signal, and we're very sensitive to distortions and don't like them. Distorted signals, not good. Linear signals, good. And so we're in a bind because we need compression, otherwise we make sounds too loud. But we must not make it too compressed, otherwise we reduce the quality too much. People don't like it anymore. Here's an illustration of these attack times and release times. And the standard now of hearing aids is that they can actually vary. So we have a fast attack and a slow attack. We've got a fast release and a slow release. Here is just a visualization. We've got an input that goes from very quiet to very loud, and it goes to very quiet and for a short time, and then for a longer time. What happens to the gain? The gain here is maximum because we have a very quiet sound. Environment becomes loud. The gain reduces over time. This is the attack time. It's usually measured as the time. This is usually an exponential decay, and the time in itself is the time that it needs to go from 100% to 50%. So it reduces over time, nice and slowly. And when the sound becomes quiet again, we increase our gain. And here it becomes quiet again, loud again, and we reduce our gain, stay there. But what's usually done these days is we measure the amount of time that the sound was loud, and depending on that, you change the release time. So for sounds that were only there very short, like the example is always the slamming door, it's very loud, but very, very short, so probably doesn't mean anything. So you want to have a fast reduction of the amplification so that it doesn't become too loud. But you want to drive up the gain as soon as it's gone, because there's no reason not to. It probably won't happen again. But if you have a long sound, input exceeds the time constant here, whatever the time constant is, it means somebody is talking very loudly, and you want over time gradually reduce the gain, and then you want to take a little bit longer to drive up the gain again, because it just sounds more natural that way. So there's a lot of parameters that you can play with, when all of these theoretically need setting in a hearing aid, because all of them affect the sound quality, mainly the sound quality sounds. It's nothing to do with audibility, just with the quality, and they all affect the perception and the happiness of the user with the device. Now, first question was how fast do we have to do the compression? The second question is how much do we want the compression to be? And there are two general options that I already mentioned. One is output limiting, so we have just a linear amplification. Just look at these black dots in here. So the input level versus the output level, we have a threshold here of about 60 decibels, so that's a moderate hearing loss. And we want to then just increase everything between 20 and 100 linearly in the remaining dynamic range here of about 30-40 decibel. That's output limiting. It means if it's too loud, we just limit it. So that would be a linear amplification as much as we can, but prevent damage at the very high amplitudes. This is as opposed, this is like an older hearing aid effectively. Newer hearing aids would rather do a WDRC, wide dynamic range compression, which means we do it, we'll talk about that in a second, in bands. And in each band we have a much steeper curve, and then the lower threshold, and then we have actually a linear, and then a compensation at the top. So we've got no gain anymore. The third question is, where do we want to do it in terms of frequencies? And we know that standard sensorineural hearing losses, here the triangles, typical one look like a high frequency sloping hearing loss. And the problem, we all should know that now, what is the other problem with the linear gain? If we amplify all frequencies the same, we also amplify the low frequencies. And the low frequencies are, as we know now, they're poison. Because the low frequencies, upward spread of masking, mask everything up in the high frequencies. So leave the low frequencies alone. Luckily there is also no hearing loss, or less hearing loss at the low frequencies usually. So we don't need to amplify them anyway that much. But the point is really not to amplify them too much in order to get the high frequencies not masked. So what is the answer to that? Not linear amplification of everything, but to put it into bands. And every hearing aid that you buy these days actually comes with bands. Any number between 4 and, I don't know what the upper limit is, 12 or something like that. And as an amplification in each of these bands. And the difference, for example, important for the low frequencies, you have little amplification. For the high frequencies, you've got more amplifications. And obviously the exact slope of these two you can set in a fitter. And it's really, there's so many parameters, and you've got how long? 20 minutes as an audiologist to set all of these parameters. So my impression of the whole thing is basically impossible to do that perfectly for each subject, for each person individually. And I've got a grant in at the EPSRC call to do something about that, but that's a story for another day. Okay, summary of the whole lecture. The loudness is related to the growth of the basilar membrane and a compressive nonlinearity due to the outer hair cells. The loudness recruitment is ubiquitous with sensorineural hearing loss. Can't get away from that. Every time you have a loudness every time you have a hearing loss, you have a loudness recruitment, so a dynamic range reduced. And any kind of outer hair cell loss leads to a loss of compressive nonlinearity on the basilar membrane. And our way to compensate for that is the hearing aid, and we attempt to replace the compression that the basilar membrane does for us. So how do we do that? We've got three questions to answer, namely how fast do they have to be, how much compression do we need, and which frequencies do we need to do that. So compression may be used in a take-home message is a good way of limit the output of the hearing aid without distortion, or with a minimum of distortion. It minimizes the loudness discomfort. It prevents further damage to the auditory system, because we don't play too loud sounds. It optimizes the use of the residual dynamic range. It restores normal loudness perception. Ideally, it maintains the listening comfort. And it maximizes the speech recognition ability. That actually we haven't really talked about, but the whole concept is how did that actually happen? These dynamic range compression, they didn't come into being just by somebody looking at the graphs, but they came into because people had problems understanding speech, mostly because the upward spread of masking and over-amplification of low amplitudes, low frequencies. That's why we need to do something to increase speech intelligibility specifically, and it has shown that the wideband dynamic compression, so we split it into bands, and individually on the basis of the hearing thresholds in each band, we amplify and set the compression ratios correct. That will maximize the speech intelligibility perception in noise. Take-home message: if you are in quiet, you either don't need a hearing aid or a linear amplification will do it for you. But if you're in a noisy environment, you suffer from the low frequencies and you need to amplify the higher frequencies more with the dynamic range compression. It reduces, final point, the adverse effects of noise. Yeah. Do you have questions? The homework for tomorrow, there isn't one. We talk about the loudness perception again on Wednesday, but I recommend that you download the IL test from Blackboard, install it on your machine, and you measure your own IL, the level, the J and D for level differences, so the just noticeable difference at say 1000 Hertz, at say 50-60 decibel. To get a feeling for what it actually is, how the experiment works, and what a 50 or a 60 decibel sound sounds like, and how well you can discriminate them from each other. Easy experiment to do, but it gives you some hands-on experience for doing that. Yes. Download IL test from Blackboard, install it, measure your own J&D, so the just noticeable difference at a frequency of your choice and the level of your choice. You can do it at several times, but it's mostly just to get for you to get a feeling for the kind of experiment. Yeah.